Hey guys, welcome to Digital Srini channel on YouTube, and if you haven't already done so, please go ahead and hit the subscribe button right now. Well, if you watched my last video, you are familiar with embedding layers. And in this video, I'm going to talk about advantages of Keras functional API when it comes to defining complex models. Now, why am I focusing a bit on some of these fundamental topics? Well, because if you would like to tackle some complex applications, for example, generative adversarial networks, more importantly, conditional generative adversarial networks, where you are providing the label values to condition a GAN, then you cannot just use your regular sequential method to define your model. Also, you cannot just go ahead and use model.fit. You may have to write your own for loops to enumerate each epoch and each batch. So there are certain things that you are required to know before we get to that topic. So I plan on actually talking about these 2 or 3 topics before getting to my GAN videos. Okay, let's jump into this topic of Keras functional API. I'm pretty sure most of you know what this is. But let's go through a few lines of code to actually put together a model using our sequential model method, and then the functional API. And then let's also look at a GAN example. Well, I'll just write a few lines of code, or I have already written a few lines of code for the discriminator part of the GAN, just to show you why we need the functional API approach. Okay, let's jump into the code and get started. Okay, so here you go. And again, our focus is on understanding functional API. So let's start by doing things that we're kind of familiar with, right? Which is using the sequential method. If I scroll down, you can see when we define a model using sequential method, we just go ahead and instantiate this. We start this model, we define a model, give it a name, and we say that, okay, we're going to use sequential method. Then we incrementally, or we add each layer to this specific model. So it knows that it's sequential for a reason, because the first one is a convolutional layer, and where is the input coming from? Well, we define our input shape to be something, right? And the next one is another convolution layer, and then we decide to add max pooling here. And then we have 2 convolutions, max pooling. And after that, we are going to flatten it and then add a hidden layer, well, dense layer in this case, with 128 nodes right there. And activation ReLU for all the internal or hidden layers. And for the final output layer, we have 10 outputs right there. Why? Because maybe this is a multi-class classification. For example, think of CFAR10 dataset or MNIST dataset where you have 10 classes, yeah? And activation is softmax because this is a multi-class classification. So this is very intuitive, easy to understand. You just keep adding one layer after the other. Nothing wrong in doing things this way. So let's go ahead and run this to have a quick look at the output summary. So let's run all of these. In fact, I'm importing some of these that we probably don't even need, like categorical, normalized, because you do these things when you import your data and get your data ready. We are just looking at the models for now. Okay, so the libraries are imported. Let's go ahead and run all of these lines. And I think we looked at everything all the way up to here. And of course, finally, you compile the model by telling it exactly what optimizer to use and what loss function and what metrics to track as we are training. And model.summary, you know that it prints out the summary on the screen. And if you watched my tips and tricks, I did this a while ago on how to print your models. If not, go ahead and search for or look for the playlist called Tips and Python Tips and Tricks, and you'll find a video on the topic of how can you visualize the models in Keras. Okay, so this is exactly what we are doing here. So let's go ahead and first of all run up to this point, summary. So there you go. Okay, so you can see here that we have 271,786 total parameters, and here it is. Here is the model. You have a convolution, max pooling, and so on. Okay, let me move on because I know most of you know exactly what this is. And if you want to visualize the model, go ahead and save it. Or I think when I do this, it should plot it on the screen. So you can see it's a very nice handover of data from input to conv, and conv to the next convolution layer, to the next max pooling, and so on. This is exactly why I prefer to use sequential method for linear models where everything is going in a very linear fashion. a layer does its job, hands over the data to the next one and to the next one and so on. If you have a non-linear way, meaning another input coming from the side and then providing input here, then you cannot do that with sequential. We'll see that in a second. Okay, but first of all, let's focus on this simple use case and then understand what we mean by functional API of Keras. It's simply in Keras. I mean, I'm adding a couple more inputs here. So one layer as part of Keras.layers is called input. And then from Keras.models, get the model. So you can actually finally compile a model or put together a model where you define your inputs and outputs. We'll see all of that in a minute. So let's not worry about it yet. So I'm going to run these two lines to import these two libraries. And when you're defining the model using the functional API, you have to explicitly define the input layer and what the shape of your input image is. This is kind of similar to here where you have input shape, but here, as you can see, you're not adding explicitly an input layer. But when it comes to functional, you have to define your input. So my input, I'm calling it input image, and this is the shape. So let's go ahead and do that. Now, as you can see, my input layer, I gave it a name, input_image. You can also name your layers here in here, but typically we don't. Here, I'm explicitly giving it a variable. I'm not naming it. Let me call it, giving it a variable name. It's called input image right there. Okay, and this is a tensor. If you look up here, it says python.keras and whatever that is and .keras tensor. Okay, so this is what we define. Next, what? After this, after we get our input, we have to add our convolution layer with 32 right there. And 3 by 3 is our kernel size. That's exactly what we are defining here. My first convolution, I gave it a variable name 1_1. This is conv2d with 32, kernel size 3, activation is relu, right? Activation is relu. But instead of model.add, I am going to say that, okay, this is going to be applied. This is the input image, whatever follows the conv2d right here is the input to this layer. So the layer input for here is the previous layer. That's it, right? So I'm adding one convolution layer, and now I'm adding a second convolution layer, which is identical to the first except for this input. So the input to my second conv layer is my previous layer right there. That's it. Now I think you got it. The next thing, what do we need to add? After con, we have to add max pooling 2D. That's exactly what we did. Max pooling 2D with a pool size of 2 by 2. And what is it working on? It's working on this. And now move on to the next level. This block. Okay, that's exactly what we defined here. Okay, and finally, after this is done, we have to send this through the dense layers, right? I mean, we are adding a dense layer right here. And before dense layer, you know that dense layer takes only vectors, so we have to flatten it. That's what we are doing down here. So the flattened layer, I gave it a name called flat. And again, the dense layer will be applied onto my flat. And finally, the output layer is basically a dense layer with 10 outputs and activation softmax, and it's applied onto my hidden one, right? So right there, very similar to this. And now that you defined all of these, now we need to put everything together, meaning we need to create a model. For that, I'm assigning, instead of calling this model, I call this model function to reflect that this is a functional API way of defining the model, and which is basically my model, right, from Keras.models with my inputs equal to this input image and output equals to my output. That's it. And remember, you can have multiple inputs and multiple outputs. This is where the complexity increases. Let's discuss that in a few minutes. But for now, exactly this model, you are defining the inputs and outputs. And this part is the same. Compile and the summary. So let's go ahead and define all of these and look at the summary. In fact, now that we printed this out, let's also print the previous model so we can have a quick look at the summary. So this is the previous one and this is the current one. First of all, the previous one, we had 271,786, 271,786. Basically, we defined exactly the same thing. Once using the sequential method and the others using the functional method. That's it. Everything else should be the same. 369 to 8 parameters, 369 to 8 parameters, 5 by 5 by 64, 5 by 5 by 64. Now, why do we do this functional? Because it gives us a lot of flexibility. If I don't want this, for example, layer to be acted on to this pooling layer, but then I want to take this convolution here, but then I want to add this pooling layer somewhere else, it gives us a lot of flexibility. And I have used this a couple of times in my previous videos when we did units and others, but now I just wanted to make sure you understand you understand this functional API in a for complex situations, especially when it comes to multiple inputs. So talking about that, let's scroll down and look at multiple inputs. So we already answered this question. So if both are giving us exactly the same type of output, exactly the same network, why do we use functional API? Just like I said, it provides more flexibility for defining the models, and more importantly, it's useful when defining models with multiple inputs and multiple outputs. And here is an example. Again, I'm not going to go through all these libraries, but let's go ahead and run these lines. And a couple of things I would like to point out right now is, you see the concatenate right there. This is because if you have two inputs and they're flowing through some path, and at some point you want to merge them or concatenate them, this is exactly why I'm actually importing that library. Other than that, everything else you should be familiar with. Okay, so let's say this specific case requires two inputs. Input number 1 of shape 64 by 64 by 1, some random shape. Input number 2 of shape 32 by 32 by 3. And some things are happening to input number 1, meaning it's followed by convolution, max pooling, and flatten. Similar journey for input 2, conv, max pooling, flatten. After this, both inputs, I want to concatenate them. That's what we are doing right there. We are merging, or we are concatenating these two, flat 1 and flat 2, these two. And then what happens? So that merge layer right there is the input to my dense layer right there, and finally I get a binary class output right there. And here is the another part where I would like you to pay attention. So finally we are putting a model together, right? Remember, we did that exactly up here when we did our model. We added our inputs equal to input image, output equal to output. That inputs can be a list of multiple inputs. That's exactly what we did down here. So if you look here, my model equals to inputs, input 1, input 2, and output is, we only have single output. Again, you can have multiple outputs. Yeah. So and print the model summary. So let's go ahead and print out the model summary here. And by looking at the model summary, it can be a bit difficult for you to understand exactly what's going on. There are like two inputs here, and there is convolution. This is exactly why we need to plot out the model so we can have a visual inspection. So let's go ahead and do that. And if you go up here, we have two inputs. And each input is going through a very similar path, meaning convolution, max pooling, convolution, max pooling. And then we are concatenating these two, and then dense layer, and then final output layer. See how nicely and how easy it is for us to define this using our functional API. Now, I'll end this video by just showing you a real use case, which we will be doing in a couple of videos from now when we talk about conditional generative adversarial networks. What do we mean by conditional? Again, I'll talk about that later on. GAN just generates images or data, right? When you can condition it using extra information. One way of conditioning that is by providing label. If you only want to generate images that look like all buses, then send a class label of bus when you're training and also when you're generating. Yeah, so that's what conditional GAN is. So please stay tuned to learn more about that later on. But this is a real case. And in GANs, we talk about embedding layer. Again, this is why I talked about it in my previous tutorial. And everything else you should know about it. You know of concatenate layer, we just talked about it. So leaky ReLU is the activation function that we use as part of, instead of ReLU, leaky ReLU here, okay, with a slope of 0.2 going down. So these are the libraries. I don't see anything else that requires any special explanation. And I plan on working on, for example, CFAR dataset, and CFAR dataset has images of size 32 by 32 by 3. So let's say my input shape is 32 by 32 by 3, and number of classes in our CFAR is 10, right? So let's go ahead and run those two. Of course, this information is required as part of my model. We'll see that in a second. Now let's go down. We have two inputs. One input is the label input, like I just mentioned, for conditioning the model. And the other input is the actual image input. Okay, so the label input has a shape of 1 right there, and we convert that into a vector size of 50 using our embedding layers, and then we reshape it, and we add a dense layer, and then we reshape it again. I'll go through these line by line when we get to that point, but just so you can see, this is how we are building our model using the functional API. So right now I have a reshaped input of my label. So I did certain things to my input label, and I got to certain place right there. And if you're curious, the output at this point would be of shape 32 by 32 by 1, because my input, that's how I reshaped it. Knowing that my input image is going to be 32 by 32 by 3, so when I concatenate, I have the right dimensions and so on. Okay, now let's go ahead and start our second input, which is the image. In our case, it's going to be 32 by 32 by 3, because that's what we defined up here. And as soon as I get my image input, I'm not doing anything to this image. You can actually add certain layers if you want, but in this case, okay, I took my image as input. Immediately, I'm concatenating my image and my label information. So this is 32 by 32 by 1. This is 32 by 32 by 3. So when you concatenate, you should get 32 by 32 by 4, because you're adding this 3 plus 1 channels. Okay, giving you a quick preview of our generative adversarial network, by the way. Okay, so now we have merged these two, and from here, it's pretty straightforward. From here, it's just convolution, leaky ReLU, convolution, leaky ReLU, and then flatten these two, flatten this, because right now we have 32 by 32 by 4, and down here you have 8 by 8 by 128 or whatever that size, and I'm adding dropout layer, and my output layer, dense layer. This is a discriminator, right? What does a discriminator do in a GAN? It discriminates between whether a real is whether an image is real or fake, right? This is a discriminator, real or fake, which is a binary classifier. Discriminator is nothing but a binary classifier. That's exactly why we have one output right there, because it's binary, 0 or 1. Activation is going to be sigmoid. Okay, so up to what point did we do? We did merge. So let's go ahead and run these lines of code. And finally, let's put together our discriminator model, which is our model with two inputs. One input is input image right there. The other input is input label. And then we only have one output, which is our output layer. And then everything else is pretty much the same. You do model.compile. And then summary. So let us output layer. Let's go ahead and print out the summary. Again, I don't think there's any point in looking at the summary, because it can be a bit challenging to understand exactly what's going on. But the whole point here is you have one input, and then we expand this input into 50, a vector of size 50, because this is an embedding layer. Yeah. Of 50. By the way, if you don't care about generative adversarial networks, then please stop this video by now, and then because you learned what you needed to learn anyhow in the first 10 minutes of of this video, or 10 to 14 minutes of this video anyway. But stay with me. I'll finish this in the next couple of minutes anyway. Okay, so this is not that much useful. So let's go ahead and plot the model so we can visually inspect what's going on. We know there are two inputs. We know that there is a embedding layer with 50 and all that. I mean, our input number 1 is going through certain stuff, and input number 2 is directly being concatenated. So if we go back up, we should see exactly that information, right? So we have our input 1, embedding, dense, reshape to 32 by 32 by 1 in our example, because my input layer here is 32 by 32 by 3, and when you concatenate those, 32 by 32 by 4, and then comes the next and the next layers and so on. So this is exactly why functional APIs can be API for Keras can be very useful. It gives you so much flexibility in defining your models. Okay, let's cover one more topic before jumping into generative adversarial networks. One other topic is how do you enumerate your epochs and batches instead of just doing model.fit and giving number of epochs and all that. You can actually deliberately write a for loop saying for epoch in your epochs, for batch in your batches. Go ahead and get a batch of images and then do some training. If that interests you, stay tuned for the next video. Let's meet again in the next video, guys. Thank you.